Okay, our next speaker is also an outstanding researcher in the field of partial differential equation. Is Matteo Bonforte. He will speak about nonlinear and nonlocal degenerate diffusion on bounded domains. He is a professor in the UAM, in the Autónoma University of Madrid. And I also want to say two key words about his work that are of my choice. I would say these two things. One is fast diffusion, and the other that I also think is important is asymptotic behavior of solutions. Thank you.
So, thank you very much for giving me the opportunity to be part of this celebration in honor of Alessio. And I would like to start this talk by saying that I met Alessio in 2007 when we were in Vienna, and he was giving probably his first course. I don't know if it was the first or the second, but and there was this body of speakers. One of them was Juan Luis, the other was José Antonio Carrillo, and then Peter Markovic. And then there was this young Figali around, which was already the people were talking about him. He was good and so on. And then after, I think, Juan Luis' talk, I saw a young guy cleaning the blackboard, and they say, oh, here in Vienna, the PhD student cleaned the blackboard between the talks. And then he started to write the title, and they said, oh, look, they are very, 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 very clever here, and very attentive. And then he also gave the talk. So, so it was probably 24, right? 23, you were 23 years old. And now that I'm 44, I hope to be able to give a talk which is comparable to what he gave when he was young. Now he's way better. Okay? So I will, in some sense, continue the talk of Juan Luis in the sense that he introduced the word of nonlinear diffusions and so on. I will be less general and a bit more specific because I will try in this talk to explain to you what Juan Luis said at the very end of the talk, no? To arrive at the point where Alessio really came into play. We had this project about nonlinear and nonlocal degenerate diffusion on bounded domain. I will try to explain you what are the problems, and the talk will be like this. I mean, I will introduce the problem, and then I will take a brief detour in 3 blackboards of about the classical porous-medium equation, because if you don't know the classic, you cannot appreciate the new, right? And then I will give you just few glance about the basic theory. I mean, just to make sure that we are not talking about the empty set. No, solution exists and they are nice and so on. And then I will concentrate on the part in which really Alessio came into play. Okay? So let's start. And the model is one of the, well, one particular choice of the many models that Juan Luis put on the blackboard in his previous talk, which is ut equal L and f of u. You have a diffusion here and a nonlinearity here. And the problem will be posed on bounded domain. So you take a smooth bounded domain, thinks the ball. The ball is perfectly fine for this talk, okay? The unit ball, for example, is a bounded domain with smooth boundary. Very good. And then you take a linear operator that can be sub-Markovian, etc. This is technical, but let me say it's a wide class of linear operator that fall into our setting, and the classical Laplacian, the god of the differential operators, fall into this class, and all fractional Laplacians on domain fall also into this class. And when I say all fractional Laplacian on domain, it was because when we started this project with Juan Luis, he said, yes, we do it on the boundary, but only if we can treat all the operator at the same time. And I asked him, why? There is more than one. And actually, yes. The answer is yes. We will see that there are at least 3 different choices of fractional Laplacian on bounded domain with 0 Dirichlet condition on the lateral boundary. And I'm writing on the lateral boundary not because I'm sloppy, but because the concept of lateral boundary depends on the operator, on the choice of the operator that you do. I will try to explain you this in the talk. And then yes, ut is the time derivative. Ut is dtu. Huh? I think that you can read also from there. Huh? So, and then as far as the nonlinearity is concerned, we can treat in general convex nonlinearity, whatever, but let's concentrate on the powers, okay? Power m greater than 1. Good, the classical porous medium type nonlinearity. And as I said, the homogeneous boundary condition are posed on the lateral boundary, which depends on the operator. And this is the setup. Okay, so now we will make a simple choice, and we will see the classical porous medium equation, and I will try to explain you, like making some picture at small time, intermediate time, large time, what happens, just to give you an idea of what happens to the solution to this problem in probably the simplest possible case. Okay, so this was meant to be on the blackboard, but since they told me the blackboard was small, I have tried to reproduce the blackboard in the slides. Then after 3 slides, you will see normal Beamer slides. Okay, so I know that it is very small there. I'm sorry, I didn't know the size of the blackboard, but I will try to write the important information here. So the choice we are doing is the following. Huh? So we are studying the porous medium equation, classical Laplacian, convex nonlinearity, I mean m power, m greater than 1. And we put, in this case it's really easy, we put u equals 0 on the topological boundary of omega. That's it. This is Laplacian of u to the m. Okay, so this is the model, and then, since it's a parabolic equation, maybe at time 0 you want to prescribe an initial configuration, which we will take for this talk, well, for this part of the talk, to be a compactly supported and very smooth function, just to see what happens. So what happens? Well, it happens that this equation is being studied by a number of people, which is written there: Aronson, Caffarelli, Bresis, Benedetto, Evans, Friedman, etc., etc., etc. All of these names, if you are in PDE, you have heard about them. Okay? The list is by far not complete, and I'm sorry if I'm forgetting people. Okay, so what happens at the initial times? What happens at the initial times is the following. You start from a compactly supported initial data. I will try to reproduce the drawing because they told me that there is not, you don't see it very well. So you start from an initial datum, say u0, like this. And then how the evolution goes. Then here you have your boundary. This is this part of the drawing. And here you have the support of u0, which is compact in omega. And then what happens? Well, the 2 key features of this equation are finite speed of propagation and diffusion. Diffusion, Juan Luis explained it in a way that I cannot improve. And the finite speed of propagation, what does it tell you? It tells you that if you start from a compactly supported initial data, then the solution will have compact support for all time. Of course, it is diffusing, so the support is becoming bigger and bigger and bigger. So what happens here? It happens that the solution, say, at the beginning does like this. There is conservation of mass, and then immediately the support of the function spreads at a certain speed that can be computed in terms of the fundamental solution, which is called Barenblatt solution, and it is basically 1 minus x squared positive part. So the Barenblatt solution is a constant minus x squared divided by time to some power, and there I put the power beta to beta, the positive part, and then you have another time outside. And this is the fundamental solution in this case for the problem on the whole space. So at the beginning, the compactly supported initial data do not see the boundary. They don't distinguish the fact that you are on a bounded domain. So they think you are in Rn, and they start to behave like the fundamental solution. So they preserve mass, and they have, say, this behavior. And here, what happens? That the first thing that you realize is that this solution is not regular where it is 0. Okay? Why? Because I forgot here the power. 1 over m minus 1, 1 over m minus 1, yes, sorry. 1 over m minus 1 is a power that when m is large is very small. And so here you have that the derivative is plus infinity and there is nothing you can do. And this is called a free boundary because it is the boundary of the support of the solution which is becoming bigger and bigger and bigger, and there the solution is really 0 and with a derivative that you cannot compute. I mean, it's plus infinity. So how do you check that this is a solution? This motivated historically the concepts of weak solution and so on, because just to check that this is the fundamental solution, you need what we call weak theories. So you know, you have to learn how to do weak derivatives and so on. So this motivated a large amount of work by many prominent mathematicians. Then you start to expand, and like the Barenblatt solution, so here you behave like in the Cauchy problem, it's if you are on the whole space. And then what happens? And then what happens? That there is a first time where you hit the boundary. So let me... okay. Yeah, so there is your domain, your compactly supported initial data, it started to spread, and at some point it touches the boundary for the first time. When it touches the boundary the first time, thank you, what does it happen? It happened that this behavior, here you have the behavior like a power, say x minus x0 to 1 over m minus 1. You have this power here, which is the Barenblatt behavior, the fundamental solution behavior. And then when you hit the boundary here, there is a change of behavior. There is a change of behavior because you pass from the Barenblatt behavior to what we call the elliptic behavior. You will understand why. So there is basically a change of power between these and these. And these two powers, m is greater than 1, are ordered. So which is the smallest? Of course, the smallest is this one. And so it means that you are concave, but with a different concavity at the boundary. Let me draw it. Let me sketch it. I mean, the drawing. When you arrive at the boundary, before arriving, you have, say, this behavior, the Barenblatt behavior. And then you have something which is like the distance to the boundary to the power 1 over m. Here you have the distance to the power m minus 1. So you pass, there is a transition from this power to this power. And this is important because it marks the difference between a bounded domain and the behavior on the whole space. So what happens after? Well, first we have to mention about regularity, a small note about regularity. The principle is that solutions are smooth when they are positive. So inside the support, solutions are smooth. Outside the support, they are 0, so they are smooth. And the problem is at the free boundary, so at the boundary of the support. And the regularity there is really a delicate issue. And there has been many works by Caffarelli, Vasquez, Volansky, Koch. And the last paper, I think, is from Juan Luis and Koch in 2019 or 18. I mean, it's very, very recent. So the problem is really difficult, the regularity at the free boundary. I will not talk about it in this talk. Okay? So then what happened? There is the transition. I mean, once you touch the boundary the first time, then the support continues to grow, and there is this transition phase in which you pass from one power to the other power, as I just explained. And then there is the second time, the T star that appears. T star is when basically you have reached the boundary in every point. I mean, when the support is spread, and you reach the boundary at every point. And when you reach the boundary at every point, somehow the problem forgets where it started from, and it starts to behave in the elliptic way. What does it mean in the elliptic way? It means that you can trap your solution between the distance to the power 1 over m, the distance to the power 1 over m, and a certain power of time. Good. So you are starting to say that after this waiting time, let's say, after T star, U starts to behave, and this means there is a constant above and a constant below, like the distance to the power 1 over m divided by t to the 1 over m minus 1. What does it mean, this? Well, it means that solutions start to behave like the elliptic equation. Where is the elliptic equation? Well, this is comparable to the solution S to the stationary problem. What is the stationary problem? The stationary problem is this is Laplacian of S to the m equal S divided by m minus 1. So the stationary problem is basically a semilinear elliptic equation. Indeed, you can write the stationary problems as follow: minus Laplace of S to the m equal constant S, or you can call this variable capital V and rewrite this equation as minus Laplace V equal C V to the P. And here the relation is that P is 1 over m. It will be less than 1 in this talk, and this is the classical semilinear equation you will hear a lot about in the next talks in the afternoon. Okay? So basically we are saying that for large times the behavior of U is elliptic divided by a certain time. And what is this? What is this? Well, this is a separation of variable solution. So you run the standard answers of separating variable and you end up with this. Okay? So what happens for large times? Well, in order to see the things in large times, what Luis was saying before, it is difficult to see it if you don't do a rescaling or if you don't renormalize your solution, because this is going to 0, this is going to 0, of course the difference is going to 0. How do I see things? Well, I do see things by multiplying by tau, and by multiplying by the right factor. And then what I get? I get that U converges to the stationary state uniformly. Okay? Uniformly. So the sup over the whole domain of U of t converges to S as time go to plus infinity. Okay? In the rescale variable, they are made and built such that you can do this separate variable solution stationary. So basically you multiply by t to this power, and you get it. Okay? So there is something better that can be said. Of course, now you look at the two solutions. This is going to 0 the boundary, this is going to 0 the boundary. So in order to see if also the boundary they behave in the same way, what do? You do the quotient. You study the relative error. You do the quotient minus 1. Quotient minus 1 going to 0, it means that also at the boundary, also where they are 0, they have more or less the same behavior. Okay? And then you can also prove rates in the sense that you can say this quantity decays like 1 over t. And this is sharp. Why? Because you take two solutions of separation of variables, and this is what they do. It's an explicit computation. So you cannot improve that. Okay? This is pretty much all, and this picture, I think, resumes what I was saying. No? In the rescale variable, the equation changes. When you rescale, you pay a price, you get a reaction term. The advantage that you have is that in this language, the function v is monotonically increasing in space for every x, and it converges monotonically to the stationary state. So you start from u0, you start to behave like the Barenblatt, the blue one, until you hit the boundary, and then you behave like the elliptic, and then you reach the asymptotic state, which is the biggest one. Okay? But what we learned so far is that, solution converge monotonically to S of x. But then S of x is an absolute bound. Is the maximum you can reach. And this is called the friendly giant. It was an idea of Dolberg and Koenig in the 80s, which tells you what is the friendly giant. Is the solution of separation of variables. You can separate variable and obtain this family of solutions. You see, capital T plus T. When you let capital T tend to 0, you get what we call the friendly giant, which is S of x divided by tau. Why we call it the friendly giant? Because when tau is 0, this is the biggest initial data that you can ever think about. It's plus infinity. And this generates a solution which dominates all the other. Okay? And represents the asymptotic state. So, what is the moral of the story? Basically, there are two behaviors. At the beginning, you behave like a fundamental solution, and then in the end, you behave like the elliptic one. And that's pretty much all I wanted to say for the classical model. Okay, so what we wanted to do then, okay, then you can improve the convergence, as I told you, in relative error, you can do the quotient and see finer things at the boundary. Good. Then let's pass to the true model we wanted to discuss here, which is the fractional model. You have already seen it, Juan Luis already introduced it. So for now, we have seen what happens when L here is the fractional, is the classical Laplacian. Now we want to put the fractional Laplacian. Okay, and the fractional Laplacian, and here the choice start to become, I don't know, you have many options, let's say. The nonlinearity, for now, we take the power, as I was telling during all the talk, and these three definitions of fractional Laplacian you have already seen in the talk of Juan Luis. I'm not going to repeat, but there is the Fourier transform 1, the hypersingular kernel, and the spectral definitions. Good. These three definitions on Rn are equivalent. It's not easy, but take a good class of function and you can check it. It's a difficult exercise, let's say. Nowadays, huh? You have to read the book of Stein to do this. It's not easy exercise. Okay, so let's see what happens when you try to adapt this definition to bounded domains. The first one that I choose is the spectral definition. So you do this semi-group thing, and the semi-group thing here is just you take the solution of the heat equation, of the standard heat equation on domains. You subtract its initial data. This is the one that starts at g of x. You subtract the initial data, you do some spectral averages, and you end up with an operator. Curiously enough, this is the same as taking the power of the Fourier decomposition of this operator. I mean, you take the power of the eigenvalues exactly as when you do powers of matrices. What do? If you diagonalize, the power of the matrix is just the power of the eigenvalue. Here is the same thing. Well, infinite dimensional. Then, one of the key properties of this is that, okay, we look at the operator, but as you have seen in the talk of Juan Luis, it's also interesting to look at the inverse operator. And the inverse operator is represented by what is called the green function, so the fundamental solution of the elliptic problem. And the green function satisfies this curious property. You see here the kernel of the green function is n minus 2s. So you can read the order of the differentiation of the operator from the green function, and then it has this part which tells you that basically you decay at the boundary like a certain power gamma. In this case, gamma is equal to 1. Why? Because this is a power of the Laplacian, and the eigenfunction and the eigenvalues are the same. They are very well known, very well studied, and we know more or less everything about the eigenfunction of the fraction of the standard Laplacian. Tell me. Yes, delta is the distance to the boundary. Sorry, there is a gamma missing there. But delta is the distance to the boundary. Yes, it was to make it fit the line. And then what are the boundary conditions that we impose here? Well, here we are in the classical setting because we are taking power of the Dirichlet Laplacian, and the boundary is just the topological boundary. No problem. Then there is what the people call the fractional Laplacian operator. We need to add a description term, which we call restricted, because we want to distinguish among them. Okay, they will have different behavior. Here what happens? You take the formula with the principal value and the hypersingular integral, and you restrict it to functions which are 0 outside omega. So the support of the function is only in omega, and then you put 0 outside. Okay, and this is why we put the name restricted to this operator. Of course, this is also a good operator, decent operator. It has eigenfunction, it has eigenvalues, and the regularity of the eigenfunction has been done by those two guys, which we'll talk later. So, one remark: the eigenvalues of this operator are smaller than the one of the other one. This doesn't have many consequences in this talk, but it's just to point out that they are really different, because the eigenvalues behave differently at the boundary, the eigenfunctions, and the eigenvalues are different, are smaller. And then the green function has a similar behavior. You see, it enjoys the same estimate if you write it in this language with the gamma, but gamma here is s, is not 1. So they have a different behavior. What about the lateral boundary condition? Well, we have said that to calculate this operator, we need to impose the G0 outside. So what is the point? The point is that here the boundary is the complement of the domain. So we have to impose 0 outside the domain. And then we were already happy with these two non-equivalent models, and it turned out that there is a third one. You take the singular integral, the hypersingular integral, you integrate just in omega, and you forget what happens outside. Okay? And this, again, is a very good operator, self-adjoint, it has spectrum, whatever. The eigenfunctions are regular, but in a different way. And the green function satisfies same kind of estimates with a different power. So these three operators are the same. Okay, roughly speaking, what is the difference? You have seen the connection. You have seen the connection between the heat equation and the Brownian motion. So particle that moves in the domain. And how do you characterize the Dirichlet Laplacian? The classical Dirichlet Laplacian in this term. When the particle hits the boundary of the domain, it is killed. So it becomes 0. Okay? So you kill the particle when it hits the boundary. And this is just the classical Dirichlet problem. And I think Einstein was the guy who saw this connection first. And what happens to the three models? So when you force the process to be continuous, so Brownian motion, you cannot do much more than this. I mean, you can change stuff and so on. But here we want to allow the particle to fly, to be able to jump also eventually outside the domains. So what is the difference in this language between the three Laplacians? Let me explain you with an example. Suppose that you are like in a domain, and you are James Bond here, okay? And you want to escape this city, because they are chasing you, and so they cannot predict where are you going because you are James Bond and you are very smart. And so what happens? You try to move around, and the goal is to exit, to escape safely. So there are three ways of, okay, in true life, James Bond will never escape, okay? Only in the movies he succeeded to escape. So how is he caught? The spectral Laplacian tells you that whenever he tries to pass the frontier or the boundary or try to go out the boundary of the city, is caught by the police or by the bad guys, or depending on the character of the movie. So you kill them on the boundary. You kill the particles at the boundary. Then there is the second model, and this is the spectral. I mean, he can jump, he can disappear and reappear in other places and so on, but always inside. Yes. Yes. He can move like this, but he can also jump, but he cannot jump outside. Why? Because you are a power of the Laplacian. So you were never escaping in the continuous Brownian motion, and you are basically jumping. You are doing the same street, say, but he can jump from here to here, from here to here, here, but he cannot jump outside in the first model, in the spectral model. In the second model, we allow him to jump outside, so it seems that he can escape, but then what happened? Just before landing, so suppose he took a plane, just before landing, they shoot him. Okay? So this is the second. This is the spectral. In the restricted, you can go here, but then you will be caught as soon as you go to the airport. At immigration, they get you. James Bond, come with us. And then there is the third model, which is called the censored model. Why? Because then you say, okay, James Bond is approaching the boundary. Yes, the censored is regional. I mean, analysts call it regional, and the probabilists call it censored because of the process that I'm telling you. Now, you arrive close to the boundary, and then there is an authority that calls you and tells you, are you sure you want to leave? There are two options. You say, no, I didn't want to leave, I just wanted to see the boundary. I said, okay, fine, nothing happens, which means that you were doing like this and then going back, jumping, whatever, but you arrive close to there, they tell you, are you sure? And you say, no, let's stay inside. Okay, let's stay inside. Well, there is 50% of probability that you wanted to go out. If you wanted to go out, they tell you, no, stop. This is a barrier, you go back to your place. and you reflect the process, and you force him to go back inside the city. So the censored is the softest. Nothing happened, but you are forced to stay in the city. You can never leave because at the border there is censorship. And this is basically the three ways of modeling these three Laplacians. And as you see, they really model different behaviors of the particle. Okay, so we will try to see these three things. Here there is a restriction which says S bigger than 1/2, which I explain it for the people that is, this is more technical, but it's because here you want to play a probability game, right? You want to toss a coin and say 1/2 I stay, 1/2 I go. But if you are in the Sobolev space H1/2, you lose the trace in L2 and you cannot play this game anymore. So what the probabilists say, I mean Bogdan, that invented this model, says that when S is smaller, then you change the behavior and it's no more Dirichlet, it's Neumann. So it's another story and I will not enter into details here. Okay, this is what happens. So far so good. How much time do I have? Good. So now let me resume in one slide the basic theory of existence. So you have this problem, and you want to prove existence and uniqueness of solution. So what is the strategy here? Well, to take advantage of the formulation that can allows you to treat all the operator at the same time. So what you pass to the dual equation. What does it mean? You apply L minus 1 here. What does it mean L minus 1? It means integrating against the green function. Okay? So the problem becomes this, and the boundary condition disappear because they are encoded in the green function. And this is the trick. So you have just the equation and what happens at time 0. And the boundary condition you don't have to care because the green function will take care of them for you. So this is why also I can be sloppy with 0 at the boundary condition, because I already know that my solution will be 0 outside in the proper sense. Okay? So we invent a new class of solution which is called weak dual solution, which take advantage of this. But let's say it's a class which contains all the decent definition of solution for those who are who know these subtleties. And we prove existence and uniqueness of non-negative weak dual solution, and then we prove that they are bounded in 2 ways. And this way is the one remembering of the friendly giant. You see, U is bounded by a constant which does not depend on U0, and then there is the time. So it's basically putting the friendly giant on top of it. Also, but these estimates are good for large times. You can do better for small times, but this is, again, technical. What I want you to retain is that existence is okay, uniqueness is okay, and solutions are bounded. So what is the next task? Okay, so far so good. With Juan Luis, we developed a theory. We wrote a number of it. Costed time and effort. It was not easy at all. But then we said, okay, what is the asymptotic behavior? The asymptotic behavior is that, okay, U properly scaled is converging to the stationary solutions, to the solution, to the elliptic equation, as in the local case, as we have seen. So basically what we are saying is that U is behaving like the separate variable solutions, which is the friendly giant. Again, S divided, solution to the elliptic problem, divided by a power of t. Good. And this suggests that if you know the boundary behavior of these solutions, ¿Cómo? Yes, the last paper we have this result. Yannick was before. I mean, it's a combination of paper you will see at the end. Sorry. I mean, this we prove for the spectral and the restricted in a paper with Juan Luis and Yannick in the CDS. Okay, next time I will do. Sorry. I wanted just to mention everybody who was involved in the project. Sorry. But, so, what is the point? The point is that S of x is what represent the boundary behavior. And we said, okay, we know the behavior of the elliptic because we did a number of well, at least one paper on that, and we want to know if the solution of the parabolic is the same as the elliptic. Answer. We were able to do it in one case, but then we didn't know what to do. We were at Austin, myself and Juan Luis visiting Caffarelli, me visiting Alessio, well, officially then sharing information, and we wanted to finish this paper and to get very nice estimate for the parabolic U close to the boundary. And we were not able to do it in all cases. And this went on for almost 1 year. Yes. What I want is to prove that U behaves exactly like S at the boundary. So let me state it in a better way. First, once you prove that solutions are bounded, you want to see if they are positive. And this is the first time in which Alessio, in this project, contributed in a very relevant way, in the sense that we were able to prove lower bounds for large time. As it happened for the local case, you cannot expect the solution to be positive everywhere immediately because there is finite speed of propagation. So you have to wait sometimes, and then at T star, solution will be positive, and you can put downstairs, you can put down and above the elliptic solution, you are happy. We were not able to do this. We were not able to do this until Alessio came into play. And I mean, we wanted to leave it as an open problem in our paper. And then Alessio solved. Yeah, it was open, and then Alessio unlocked it the very same afternoon. So this was this was quite problematic for us. And then we say, okay, we rewrite the paper from scratch, and we write the theory in a different way. And these are the paper with Alessio. And Alessio did what I started to call before, what I call figallata. What is a figallata? Figallata is something you expect to be true, you really want to be true, and you have no idea of how to prove. You tell Alessio, and he produces a proof in finite time. Okay? So this is, there is an improvement to this, because this was before 2018. Xavi will tell you in his talk the improvement of the figallata. Okay? So this was first Alessio figallata. He gave us what we call a universal lower bound, because it holds for all the operator we are talking about, and, well, a larger class of operator. We did more general theory indeed. And what does it tell you? It tells you that you can immediately put a positive function below your solution. So you are instantaneously positive. What are the consequences of this? Well, there is a big difference now between the non-local case and the local case. Why? Because we have seen that in the local case you have finite speed of propagation, so you have to wait time before being positive everywhere. Here you don't have to wait nothing. As soon as T is positive, solution is positive. And in a quantitative way. So it was able to quantify the infinite speed of propagation. That there was infinite speed of propagation in the Cauchy problem was proved by Juan Luis, Arturo, Fernando, and Anna. We know it in a qualitative way. They do a very delicate moving plane argument. It was a very complicated proof indeed. I mean, it's very difficult to prove this. Here we succeed, thanks to Alessio, to put an explicit function below. I mean, this information is really... Then the problem is this power the correct one? The answer is both yes and no. It depends on the operator and on the data. And this is a surprise, because in the porous medium equation, you wait some time and then you stabilize. You have that behavior at the boundary and it doesn't change forever. So, in the good case, so in the restricted and in the censored, well, you can prove this. You can prove that you have the same power below, the same power above. That's it. And this is what we call the global Harnack principle. I mean, there is a remembering of what was happening before, because you see here you have dependence on this quantity, say on the initial datum, until T star. And then you forget. Like before. Until you reach the boundary, you remember about the initial data. And then, once you have reached the boundary, you start to behave like the elliptic and you forget about the initial data. The same thing is happening here. These constants do not depend on you. So when t is large, you become elliptic somehow. And what is the best way of expressing this? The best way of expressing this is in this way, like Alessio was telling before. You take the quotient between you and the separate variable solution, and they go to 1 with an explicit rate, which is 1 over t. And this result also applies to the classical case with a more quantitative proof. I mean, it was first proven by Aronson and Pelletier in 81, then Juan Luis gave an improvement in 2004 for more general data. We cannot generalize Juan Luis' work because it was already sharp, but this is an alternative proof of the result by means of the previous inequalities, of course. It's a quite easy corollary here. And then, what happens in the bad case? What happens for the spectral? And for the spectral, it happens that it appears this weird exponent. Exponent sigma begins, and you see it's a mixture of S, which is the order of derivation, M, the nonlinearity, and gamma, the boundary behavior, which in this case is 1. I just put it here because I wanted you to see that all the components enter into play. And you have to discriminate when this quantity is bigger than 1 or when it's less than 1. And there is a problem because here you have the universal lower bound that I told you before. And here you have the best upper bound that you can provide. Okay, after we did with Alessio this lower bound, we were saying, okay, can we improve the lower bound to match the upper? Answer, no. Can we improve these to match the lower? No. But what is the point? The point is that, look, here you have the asymptotic behavior in the quotient, but if you remember what I told before, this is happening always. So U is converging to S, so you expect also the boundary a similar behavior. And this was our conjecture, which was actually wrong. I still remember I was talking to Alessio. We were trying to do the proof of this result to find the matching powers, and he was going to see his wife in Cambridge at the time, right? And we were taking the plane from Zurich to and he told me, Matteo, try to do this. And then when I arrive in London, I call you back and you tell me how it is. And I say, okay, I'm not you, I cannot do this computation in 2 hours, but I will try. And then computation, there was a mistake moving in the computation, so were, again, not possible, they were wrong. And I told you, Alessio, unfortunately, also this proof doesn't work. He said, better, because I have a counterexample. So I am happy I didn't do the mistake in my homework. But what happened is that really the idea is the anomalous boundary behavior when this quantity is less than 1. What means? It means that S is relatively small when there is very few diffusion. So the speed of propagation is still infinity, but the idea is start from big initial data. If you start above the stationary solution, by comparison, you will be above the stationary solution, so you have the same power, below and above. So this was the thing that was really bothering us, because we know a class of data, say big data in another sense, that what is commonly used today, but take large data and you will have the behavior you expect. So what happens? Then on the other end, the asymptotic tells you that yes, you should behave in this way. What is happening? It happens that if the solutions are small, and this is the second figallata, when data are small relatively to the first eigenfunction, say distance to the boundary, compactly supported, as the example I was showing you of the porous medium. What happens? That, okay, this upper bound, this improved lower upper bound holds, but be careful. When we are in the bad range, so when we are in the range in which anomalous behavior appears, the quotient between the stationary solution, this is another way of rewriting it, the stationary solution and the solution is always 0 for every time. And so you jump at 1 only at t equal plus infinity, which is something that numerically you cannot check. And indeed, we did numerical experiment, which will be the last slide. And yes, I'm almost done. We will see numerical experiment in which exactly you see that you can never verify that they are one. They're always different. Well, numerically. And theoretically too. Then we said, okay, so maybe this is the sharp power. We can prove upper and lower bound also for this. So this was second hope. Then there was, well, second, third figallata of the program, which is the second counterexample. So Alessio was not happy, so he said, okay, let's take a small initial data, and let's say, assume you prove the lower bound you want. Well, if you prove it, it's false, because there is a limitation on the exponent you can obtain here. And I was really impressed when I saw this, because he told me, suppose that your bound is true, and then alpha has to be big than this strange number. But what does it mean? It means that alpha is bigger than 1 over m, which is bigger than sigma over m. So you will never get the right power. And if you do, you made a mistake. I'm happy that in 2 years I never did this mistake. But of course, I'm also happy to have learned one thing, which I think it's very important. And you learn really these things I learned from Juan Luis and from Alessio and from them, that when something is wrong, first for us is better. We are the only scientists which are happy when there is a problem. Second, that if you insist in proving something, well, maybe you should start, and it doesn't come out, and it doesn't, maybe it's a good idea to start to prove that, to try to prove that maybe this is wrong. And this was, I mean, I was not young when I was doing this. I mean, Alessio is always younger than me, but the point is, I learned really this lesson, and I'm very grateful for that, because, and I teach it, I try to teach it also to the PhD student, but be careful. You have to try for 2 years, and then you can start to think that it is wrong, okay? So this is the main point. So, well, we did, Alessio did this second counterexample, and then, so the problem, so what is the best lower bound that you can put? The universal one. And so really, this theorem that we have seen here, which was a priori not sharp, it turns out to be sharp. Because there is nothing better in general you can do here unless asking something more on the initial data, and there is nothing better you can put here unless asking something more on the initial data. And so, are these estimates good? Yes, more or less as the other one with matching power, because they allow you to prove interior regularity. They allow you to prove solutions are classical, they have C2 alpha, whatever, the equation makes sense point-wise, good. And then the problem is, can I prove the estimate in relative error? Of course not, because of this. So the relative error will never converge uniformly to 1, because it's 0 at the boundary, and it will be 0 forever. It jumps to 1, there is a discontinuity only at infinity, which is very difficult and very subtle to see. And this is why we are so proud of this part, which was surprising to us, and I hope I was able to transmit you that it was really delicate and difficult to see. And without Alessio, I'm sure, I mean, we wouldn't have seen it. Huh? So thanks. Then I will show you some numerical simulation that Juan Luis, he went to the Beckham, and there was Felix, which was Felix Del Teso, which was former student of Juan Luis, and he was doing numerics with this group led by Gerardo Gioda, and they did for us the numerics. So this is the good case. You see, you start from a compactly supported initial data, and then here you don't appreciate here because the definition is not so good of the image, but you see that at time t equal 5, which is very small, you already cannot distinguish the boundary behavior between this and this. This is the stationary state. It's in a scale variable, and so on. Then, and this is the good case. Is the good case. So here I want to compare, for example, the good case with the bad case. Okay? So you see, in the good case, you get, this is the same picture as before, you cannot distinguish the boundary behavior, but here, yes. Here, yes, you will see that the boundary behavior is really different for all times. I mean, we waited until t equals 600. which means a few days of computer running. And this is only 1D. I mean, it's really quite delicate, the numerical approximation here. And what the people, okay, what is the moral of the story? I mean, here you see also that you cannot reach the true power, and you are forced to stay in this anomalous power of the second counterexample. Okay, but what is the moral of the story? What the people doing numeric was telling us: without your prediction that this weird behavior can happen, we think we didn't do the numeric properly. Because if you don't see the proper boundary behavior, it means that your numerics is not good. Maybe you have to choose a finer mesh or another method or whatever. But no, it's not that the numeric is not good, it's that the equation has an anomalous boundary behavior. And with this, I just wanted to thank you very much for your attention, congratulate Alessio for this Dr. Honoris Causa prize, or honor, and thank you very much for working with us all these years, and I hope this collaboration will continue forever. Okay?